Hello friends, welcome back to our channel Adami Education. Hope you are all doing well. Today we are going to continue with the chapter Reflection and Refraction of Light. So last day I told you that we are going to learn about another important point, focal point or focal length in the later class. So let's begin with that. So over here I have the diagram of two mirrors. The upper one is a convex mirror and the lower one is a concave mirror. Let's see what is actually the focus or the focal point. So according to the definition, when a parallel beam of light which is parallel to the principal axis is traveling, it will always converge on the focus, or it will appear to converge on the focus. So what does this word appear to means? In case of a virtual image, that is for a convex mirror, we need to focus on the appearing point. It will not be a real image, it will be a virtual one. So the ray of light will appear to converge, it will not happen in reality. So let us understand this fact. So I'll explain the concave mirror first because it is easier. A parallel beam of light which is parallel to the principal axis is moving like this. So after reflection, what will happen? It will pass through a point. Similarly, if I have another parallel beam of light, after reflection, it will again pass through the same point. So if there are multiple parallel lines, I am not making them out here, otherwise it will look very clumsy. So if there are multiple parallel lines which are moving, or parallel beams which are moving parallel to the principal axis, they will always meet the focus, or they will always converge at the focus after reflection. Since they are actually meeting, this will form a real image. Okay, so this point where the two rays in this case are meeting, this is known as the focus. And what is the focal length? The distance between the pole of the mirror and the focal point is known as the focal length. It is also denoted by the symbol small f. Now coming to a convex mirror, what happens in this case? Since you have studied in the previous lecture that a convex mirror does not form a real image, it will always form a virtual image. That means the rays of light will not actually meet at the focus. They will appear to meet if they are produced in the backward direction. So let's see. I have two parallel beams of light which have stricken the convex mirror surface. After reflection, since this is a diverging mirror, it will get diverged. Both of the light beams will get diverged. But if through dotted lines I am producing it backwards, I am going to see they will converge each other, or they will connect with each other at a point which is actually the focus in this case. So the rays are not actually meeting, but they appear to meet. So in this case, this length, the length between the focus and between the pole of the mirror, this is known as the focal length. So focus has two definitions, one in terms of convex mirror, one in terms of concave mirror. So make sure you are writing both of them if it has been asked, or if it has been asked specifically, you can write accordingly. In case you are worried about which one to write, I will suggest you write both of them, not to leave any option for the examiner to reduce your marks. So I hope the concept of focus and focal length is clear. Using this, we are now going to study about the various types of rules which we use to make ray diagrams. The first rule you have already come across in the previous slide. Whenever a ray of light is traveling parallel to the principal axis, it will always pass through the focus. Either it will for sure in real, in the other case it will appear to meet the focus, but at the end it will always touch the focus. So this is the first rule. So let me consider a concave mirror. So this is the principal axis. A ray of light which was moving parallel to the principal axis will always pass through the focus. Always. This is a fact. This is going to be used when you make the ray diagrams. Now, a very similar rule, which is just the opposite of the previous one which you have just seen. If a ray of light is moving through the focus, it will become parallel to the principal axis. So basically these two are just the inverse of one another. So let me just recapitulate it once again. If a ray of light is moving parallel to the principal axis, it will move through the focus after reflection. If a ray of light is moving through the focus, after striking the mirror, it will become parallel to the principal axis. Now coming to the third. So we have a concave mirror here with the principal axis. So this is the focus. There is another point, that is the center of curvature. Last day we have studied about the center of curvature, and it has been observed that focus is always equal to half of the radius of curvature. The distance between the center of curvature and the pole was known as the radius of curvature. So focal length, the focus is always situated midway between the pole of the mirror and the center of curvature. Now, if a ray of light is moving through the center of curvature, even after reflection it will move through the center of curvature. It will not change its path. A very, very, very important observation which we will use extensively in our ray diagrams. And finally, we have Snell's law of reflection, which we have studied earlier. If a ray of light, this is the pole of the mirror, if a ray of light strikes the pole with an angle of incidence I, it will reflect with an angle of incidence, with an angle of reflection R. And you know angle I is equal to angle R according to the laws of reflection. Okay, so these are the rules which we will use while making the ray diagrams. Now, before we start with the ray diagrams, there is something that you need to understand. In reality, there are multiple rays which are actually forming the image. But for the sake of clarity, we are just going to use minimum 2 rays for understanding image formation in the different types of mirrors and later the lenses. Okay, this doesn't signify that only 2 rays are essential for formation of a crystal clear image. Actually, in real life, there are numerous rays coming. But just for our diagram to be clean and understandable, we are using 2 rays only. So we are going to first confine our studies of ray diagram to concave mirror. So let's see. So for every ray diagram, make sure you're also noting down the position of the image, the size of the image, and also the nature of the image, whether it is real or whether it is virtual, whether it is magnified or whether it is diminished. So the word diminished means it is smaller in size. Alright. So this is our concave mirror. Let's begin. In the first case, the object is at infinity. That means the object is very, very far away. We don't know where. So we will assume that the rays of light which are coming from the object are parallel. Because it is very far away, so we will assume, like we know, since the sun is very far away, we assume that the rays of the sun are parallel to one another. Similarly, if the object whose image we want to form is very far away, we will assume that the rays coming from it are parallel to one another. And as you know, 2 parallel beams or parallel beams of light, when they strike the mirror, they will always pass through the focus. So in this case, the object is at infinity and the image is formed at the focus. As you can see in the diagram, the image is formed at the focus. So how will we understand the position of the image? Where the 2 rays of light will meet. That is the position of the image. And what will be the nature of the image? As you can see, the rays are focusing at a point. That means the image will be highly diminished. That means it will be very tiny. Highly diminished. Since it is a concave mirror, it will be virtual. That means it will be inverted. And since it is virtual, it will also be, I'm very sorry for the folly. It will be real because it is a concave mirror, and since it is real, it will be inverted. Okay, I guess you understood. Since it is a concave mirror, you know a concave mirror forms real image in all the situations except for one, which we will learn at the end of the video. But in all the other cases, it will always form a real image, and a real image is always inverted. That means if the object is like this, the image will be in the opposite fashion. So this is the first ray diagram for a concave mirror. So now considering the second case of formation of image by a concave mirror. So in this case, the object is on the focus and the image will be formed. Let's see where. So let me consider the object is here on the focus. So this is my object. This is my object. Now, the first beam of light that we will consider will always move parallel to the principal axis, and we know whenever a ray of light is passing parallel to the principal axis, it will pass through the focus. In this case, the second ray that we will consider will be passing through the center of curvature. We have to pass it in such a way that it touches the upper edge of our object. So we know whenever a ray of light travels through the center of curvature, it will retrace its path and come back in the same way. So what are the positions of the image? What do you think? As you can see, the image is not formed by the intersection of lines, right? Rather you get a parallel beam of light. So what do you mean by a parallel beam of light? You have just studied in the previous slide that whenever there is a distant object, an object at infinity, it will appear to emit parallel beam of light. So now if the image is depicted by a parallel beam of light, that means the image is at infinity, just the opposite of the previous one. So in this case, the image is at infinity, the object is at the focus, and in this case, what will be the characteristics of the image? In the previous case, we saw that it was highly diminished. In this case, the image will be highly magnified. So basically, the previous case and this case are just the opposite of one another. Highly magnified. Alright. Similarly, since this is a concave mirror, it will be a real image and it will be inverted. So let me give you a small tip while learning these ray diagrams, which appear to be really difficult right now. Learn the rules first, the position of the object and the image, and accordingly when you make the diagram, you can easily remember the rules and manipulate your diagram accordingly if there is a mistake. But after years of practicing, you will realize that you will have no option for making mistake because it will always be perfect. Now coming to the third ray diagram. In this case, the object will be between the focus and the center of curvature. So let me just mark them, focus and center of curvature. So during your exams, make sure you're using scale, but just putting the position of focus and center of curvature does not require any specific mathematics skill. You can just do it according to your eyesight. If it looks correct, it's fine. Now in this case, the object is between the focus and the center of curvature. Let's see where the image will be formed. The first ray will move parallel to the principal axis and it will pass through the focus. The second ray, we are not going to use the center of curvature. We are going to pass the second ray through the focus. And you know, whenever a ray moves through the focus, it will become parallel to the principal axis. So the ray meet at this position. So the image is formed beyond the center of curvature, that means away from the center of curvature. And as you can see from the diagram itself, the object is smaller as compared to the image. That means the image is magnified. So the image is formed beyond the center of curvature. The object is between focus and center of curvature, and the image is magnified. Don't write highly magnified, it is just magnified. It is real and it is inverted. I guess it is clear. Next, coming to just the opposite of this ray diagram. In this case, the object will be beyond the center of curvature, and as you have guessed it by now, the image will be formed between the focus and the center of curvature. Let's see. So let me quickly point, the focus and the center of curvature. So in this case, the object is placed beyond the center of curvature. So the first ray will move parallel to the principal axis and hence it will pass through the focus. The second ray will move through the focus and become parallel to the principal axis. Since I am making it directly on a white screen, you might find a little bit, you might find some discrepancies in the diagram. Let me just correct it for you so that you can understand it perfectly. When you use a ruler, there will be no such discrepancies. You will get the exact correct image. So the image is forming here. As you can see, the size of the image is smaller than the size of the object, and like we guessed it previously, the image is between the center of curvature and the focus. So in this case, the image is between C and F. Object is beyond C, so it's just the opposite of the previous ray diagram. And in this case, again, the object is real, it is inverted, but it is smaller than the object, as you can see. So we are going to write it is diminished. Alright. So the first 4 cases were just the inverse of one another, as we saw. Now the easiest one, which you don't have to work too much hard on, the focus and the center of curvature. If the object is on the center of curvature. Alright, so essentially according to the facts, the image should form on the center of curvature. So without much delay, we are going to make a similar sized object on the center of curvature and then proceed with the ray diagram. In this way, it becomes easy for you to prevent any mistakes. So the first ray travels parallel to the principal axis and it will move through the focus. The second ray will move through the focus and become parallel to the principal axis. So as you can see through my dangerously mangled diagram, but when you make it on the answer sheet or in your copy, make sure you're doing it clearly. The object and the image are formed on the same point. That is, the object is also at C, the image is also at C, and the size is exactly same. Size same, no diminished, no magnified. That means no magnification is produced. The size of the image remains same as that of the object, and again it is real and inverted. That remains constant. Now coming to the last ray diagram for a concave mirror, which is the most different, because in this case, this is the only case where a concave mirror forms a virtual image. Let's see. So for this to happen, the object has to be placed between the focus and the pole of the mirror. Let's see. The object is placed between the focus and the pole of the mirror. So again, the first ray, let me use a different color. The first ray will travel parallel to the principal axis and it will pass through the focus. The other ray will be moving through the center of curvature, because in this case the image will be formed on this side, right? So let me make a ray which travels through the center of curvature, and since we know it will travel back in the same direction. So as you can see, the rays of light appear to meet but behind the mirror. So we are going to make some dotted lines to form the final image. So the image is formed inside the mirror, and that too, it is a virtual image. So this is the most interesting case of ray diagram in case of a concave mirror. So the image is formed behind the mirror. If you are unable to remember this word, you can just say inside the mirror, and the object is between the focus and the pole of the mirror. And as you can see, the image is magnified, the image is virtual, and it is erect. It is not inverted. So this case is used in magnifying glasses. All the magnifying glasses use lenses nowadays. We can use a mirror to be used as a magnifying glass as well. So this is that case. Okay. So this is the end of the ray diagrams of concave mirror. So different positions of the object are used for different phenomena. Like for example, the first one that we learned, where a parallel beam of light was forming the image at the focus, it is actually used to burn a piece of paper, or concentrating all the solar rays into one point to generate energy. Okay. Now coming to the one and only diagram, ray diagram of a convex mirror. Let's see. So we know a convex mirror will always form a virtual image. Whether the position of the object is anywhere, it will still form the image as a virtual image. So let me make an object. Same. A parallel beam of light will move from the object, and since we know it is a diverging mirror, it will diverge. The ray of light will appear to meet on the focus. The second beam of light will be directed towards the center of curvature. So since it will not actually meet, it will go and come back in the same manner like we have studied. So this is the position where the rays are meeting, and this is the position of the image. Clearly the image is of smaller size as compared to that of the object, and also it is virtual and it is erect. So this is the only ray diagram that you will observe in case of a convex mirror, and this mirror is used in the rear view mirrors of cars. That's why you are able to see virtual images but smaller images, so that you are able to get a wider view. So these are So these are the ray diagrams that is present in the chapter mirrors. In the next lectures, we will also focus our ray diagrams for lenses. You will see that the rules and regulations are exactly the same. So I guess you have understood till here. Hopefully you will understand more in a much better way when you do it yourself in your copy, and I would advise you to use a ruler so that your lines are clear. And also one more thing, please go through the rules before you make the diagram. It will make the process much more easier. So hope you have understood. Let's meet in the next class. Till then, keep studying well. Bye everybody.